All right, let's begin. Your next homework assignment's due on Tuesday, and as per usual, you should upload your PDF file to MU Online before class begins, so you'll have till 11 o'clock on Tuesday for that one. I wanted to point out that in MU Online, if you haven't already, you can print out the class notes from there. Let's just take a quick look at what's available on MU Online right now. Also, the grader has started finishing grading your assignments and posting a solution there, so I wanted to mention that. Okay, so here's 318, that's our class, and so the lecture notes are available in a variety of different formats. If you want to have 3 notes per slide, then with no lines, that's a printing option, or if you want them to be bigger, then you can go back and choose it so that there's only 1 slide per page and so on, all the way up to 6 slides per page. So these are the notes for the entire semester, and you can get those and print those out. The other thing is the homework solutions. The author of the textbook has copyrighted their homework solutions, and so I can't post like the textbook solutions online for you to look at. And so instead of that, what I've asked the grader to do is to post her solutions from last year. And she's actually, her solutions got progressively neater and neater through the semester, and by the end they were like these beautiful documents of neatness and clarity. And so I would be happy to have you following the example of this student in solving your homework. And I was also fairly confident that she did all this work herself rather than consulting any sort of an online manual. So I know all of the steps are there. So since there are so many students in the class, we've got 50 students this semester, it's not possible for the grader to give every student really detailed feedback on every step of your problem. So unfortunately, that burden of sort of figuring out what you did wrong shifts to you. On your homework, if you don't have full credit on one of the problems, what I'd suggest you do is compare what you did to the solution that's posted. And actually, I think that can be a pretty useful learning experience, you know, deconstructing what went wrong if you have a mistake on one of the problems. At least I hope it is. So I wanted to point out that you can find your score in the grade book, and the grader sometimes does give you some written feedback telling you which problems you did wrong, and on which problems you should take a look at these posted solutions. Occasionally, even this great student made a few mistakes, so you'll notice which problem was it here. All right. So last semester when she was doing problem 237, she only got 10 out of 15. She has corrected that, and here's the updated version of 237 with the correct solution. So, any questions on kind of the workflow for homework this semester? You solve it, you scan it, upload it. The grader will give you some typed comments, and you'll see your score in the grade book, and then it's on you to understand the correct solution, which will be posted in that folder, homework solutions. All right, so back to these announcements then. Tuesday is when homework 3A is due. And although only 10 assignments are required to be submitted through the semester, I'd encourage you to solve all of them, or at the very least look at and really understand the solutions that are posted for all of them. All right, so today we're going to continue talking about manometers. In class last time, we introduced the most basic type of manometer, which is just a piezometer. But today we'll look at some more useful and functionally appropriate manometers. And then we're also going to talk about atmospheric variation in pressure. All right, so here's the original YouTube. Everybody knows what YouTube is. Before there was YouTube, there was YouTube. And this is a means of measuring pressure that will work even if the fluid flowing through a pipe is a gas. And you'll remember that when we were talking about piezometers last time in class, I said the way it works is we have some pipe and a fluid is flowing through the pipe, and if we puncture the pipe, then stuff would start spraying out if it's a liquid. And so instead of allowing that, we connect a secondary tube that goes up, and then the water level will rise to a certain elevation consistent with how much pressure there was inside of the pipe. Now let's assume that this secondary tube here is made out of steel or plastic, something where we don't have to worry about the capillary effect. You know, we already discussed the capillary effect in the lab this week, and the capillary effect is pretty pronounced if it's a small diameter tube. Even if it was glass, if it was a large diameter tube, then we wouldn't have to worry about the capillary effect. But in any case, the relationship here is that delta H is observed, and we can find out the difference in pressure between the center of the pipe and the atmosphere that this piezometer is connected to. The difference in pressure is indicated by delta H times gamma. So this was the simplest means of measuring the pressure, but it wasn't good for a lot of reasons. Number one, because we were talking about how that delta H would be really big for typical pressures in a water pipe network. And the other problem being, since it's open to the atmosphere, gases can just flow out. This U-tube manometer is going to solve both of those limitations. So we could have a liquid or a gas flowing through the pipe, and the fact that we have some manometer liquid that's trapping the gas or the liquid from coming out into the atmosphere allows us to overcome the problem we had before with gases. And having a separate manometer liquid from whatever liquid is flowing through the pipe, let's say we make this mercury, and then it was oil or water flowing through the pipe. If we used a relatively dense liquid inside of the manometer, then this delta H, the deflection distance, doesn't have to be as big. And so whereas we maybe would have 50 meters of water to measure in a piezometer, if we use mercury, then it may just be a couple of centimeters that we have to measure the deflection in order to characterize the pressure. Okay, so that's the big idea with how these work. Yes?
I have a water pump in an aquarium that looks similar, except the little hose coming off the top is on the side, and if you open the little valve on that hose, it actually sucks in air instead of water rising up through that line.
Thank you.
How does that work?
I don't know.
It's literally the opposite of that, but
Yeah.
it's the same mechanism.
Yeah, so water is going into the main pipe?
Water flowing through the main outlet, and then that little hose on the top has a valve on top. When you open it, the current sucks in air through that hose.
Yeah, I'm not sure. Maybe you can bring in a picture of it. I'd like to see a photo
Sure.
to know.
It's like literally the opposite of that.
Yeah. In this case, we're assuming that we have a positive pressure inside of the pipe. And so the way that we would measure that positive pressure, so if it was a suction pressure, maybe then air would be going in. But here, since it's a positive pressure, the way that we find out how much it is we start where we know something. And what we know is the atmospheric pressure. So, you know, this is open to the air at 1 already. There's no valve closing it off. So if it's air in contact with this manometer liquid, then we're just going to be applying the accounting principles of delta P is delta H times gamma. So we start at 1, where we've got atmospheric, and then anytime we go down through a fluid, the pressure is increasing, right? So from 1 to 2, we could say basically the pressure at 1 is 0, gauge pressure, because we're measuring things relative to the atmosphere. And then the pressure at 2 is whatever the pressure was at 1 plus delta H times the gamma of whatever fluid we've gone through. And here, the fluid is some manometer liquid. And so I'm going to say gamma sub m. How does the pressure at 3 relate to the pressure at 2? They're equal. How come? Equilibrium? Same elevation, same liquid. Now, I want to be sure that everybody gets this. Same elevation doesn't mean same pressure always. For instance, here at 1, the pressure here and across from that is not the same. It's only the same pressure if between them, you're going through the same fluid. So think of it this way. At 2, we've got some pressure, and then as we go down, the pressure is increasing, but as we go up, the pressure is decreasing the same amount because they're at the same elevation. So it's true that P3 equals P2. But the reason it's true is because between those 2 points, we only went through the manometer fluid. It's an important distinction. All right, so following this approach, what should we say for P4? P4 equals what? Okay, so L is going to be the distance here instead of delta H. So it's going to be L and what else? Times gamma. All right, we're heading the right direction, but you said plus. I was a little worried about that. Should we add or should we subtract?
Subtract.
Why subtract?
Because the lower you go, the more pressure increases.
All right, yeah. So as we go up from 3 to 4, the pressure is decreasing. All right, so good. P3 minus L, which is the relative distance that we're going, times gamma. Now in this case, it's not gamma M. It's the gamma of whatever this fluid is. If it's water, if it's gasoline, kerosene, whatever it is. But we need to distinguish between the manometer fluid and then the fluid that's in the pipe. All right, very good. So let's put some real numbers in here. I'd like you to get a try with this approach. Find out what is the pressure at the center of the pipe. If it's 10 degrees Celsius water in the pipe, and to save you from looking that up, let's just assume 9810 is our water. Gamma of water, 9810 newtons per meter cubed. And now I've given you an S for mercury. S in some text is meaning the same thing as specific gravity. So it's the ratio of either the unit weight or the density. It's the ratio of that to the ratio of water. All right. So every problem should start with a sketch, no matter how sloppy and embarrassing. So there's my sloppy and embarrassing sketch. I hope that you've got a steadier hand than I do. Also, you'll notice that up here on the side, I kind of do some preliminary stuff that, I establish the unit weight of water I'm going to be using. I calculate the unit weight of mercury based on the specific gravity that was specified. So this is just kind of like laying the groundwork. Sometimes if you don't know how to start a problem, just doing a sketch and stating the constants, kind of like you're stalling, you're stalling for time. And then sometimes it'll come to you once you take the time to do the drawing and, I don't know, fake it till you make it. So now we just do it step by step. This is almost like accounting. You start where you know something. The gauge pressure of the atmosphere is 0 at 1. And then we're going through, and as we go down through the fluid, the pressure accumulates. And so the interface of 2 and 3, the pressure is 60 kilopascals. And then the pressure decreases as we go upward from the segment from 3 to 4. And ultimately, the pressure at the center of the pipe, 42.1 kilopascals. All right, so any questions? Yes?
So if we were to find the pressure like in the middle of the curve there, would it be the same, just the same length, or is there a special way to do that?
Good question. So you're saying if we had found the pressure at the bottom down here? Yeah, we don't know how far that is since it's not dimensioned. If we were given a distance, then we could find the pressure there, and we just simply use the vertical component. It doesn't matter side to side how long it is. It could be a mile wide and the pressure would be the same, which it brings up a point. Like scuba divers, it always confused me when I was younger, when you'd sometimes see people diving in caves. And I always, in my mind, I wondered, like, if you're going down in a narrow cave scuba diving, is the pressure the same as if you're in the ocean? You know, and it is. It doesn't matter how wide the container of water is. The pressure only depends on the vertical distance. And so a scuba diver 100 meters down in a cave is going to be experiencing the same pressure as a scuba diver 100 meters down in the ocean. 100 meters is pretty deep. You'd probably be crushed, but I don't know. Other questions related to this example? Yes?
So our answer gave us gauge pressure, right?
Oh, very good question. Yeah. It's gauge pressure. So what if it had said, what is the absolute pressure at 4? How would your response have been different? How would you convert that gauge pressure into the absolute?
Add 101.
That's right. So you just add 101,325 pascals, and that's the difference between gauge and absolute. Good. All right. Well, let's take this to the next level. Let's up your manometer game. All right, guys. Let's up your manometer game. This looks confusing, right? I love confusing little drawings like this. It's partly about the dimensioning. It's partly about the zigzagging. All right. But you do have everything you need here with the hydrostatic equation. So we want to know what's the pressure at the center of the pipe. Okay, so the center here at A. Going into the page that we don't see is a pipe, and they've got this manometer, a very circuitous manometer coming off of it. And so we're going to do the same thing where we start where we know the pressure, which is at the interface of the atmosphere and this first layer of water. And I would suggest that you label interfaces. And so there's 1, 2, 3, 4, and so on, so that you can calculate the pressure at different waypoints along the path towards A. All right, so I'm going to do the same thing. I'm going to pause the recording. I'm going to circulate around with my answer, and hopefully you'll see all the little tricks in the road here having to go with the dimensioning. I guess just to standardize what we're doing, I've labeled some of these points. And this is a bit different from the previous example where we went from 2 down to some location, then over again. I'm just saying that since it's on the same elevation here at 3 and across from 3, I'm going to not label that intermediate step. Yeah?
So why is the 30 centimeters labeled twice?
It's because you're going to need to know that distance to get from 3 up to there.
Oh.
Sometimes there's no reason at all. In this case, there is. Sometimes it's just for no good reason. But here you do actually need it separately labeled. You're going to need to bring in your binoculars to class if you like to sit on the back row, because, man, that's awfully small. Let me. 89.5. It is 89.5 kilopascals. Let me zoom in a bit. That's ridiculous. I just don't want to zoom in too much on this awful drawing. I need to increase my Parkinson's medication or something. I don't know. All right. So we do a sketch. We do some of our preliminary calculations over here. Find the unit weights we're going to need, and then just the accounting begins. The pressure at 1 is 0, then we calculate the pressure at 2. Now, you'll notice that, like, I've got these little brackets here where I show what's the result of this multiplication. That's a habit I developed when I was in college because I had unlimited time on exams. Are you jealous? I had unlimited time. All of the exams at my school were usually given in this testing center, and the way it worked was the professor would say, you need to go take the exam on Wednesday or Thursday, anytime you want. You know, the testing center would open at 5 a.m. and it was open till midnight, and you could just go anytime you want. And most professors didn't put time limits on tests, so I would quadruple check all my calculations. There's no way I was going to lose a point because I multiplied something wrong. And I just got in the habit of doing like these really detailed step-by-step confirmations that I wasn't making any mistakes. And you definitely don't have unlimited time on your exams, but still a good habit to where you can double-check your calculations. And if you make these little notes like that, then it'll help you to spot where maybe you went off the rails if you don't get the same answer when you double-check. So the pressure is increasing as we go down, thus the plus here. Plus, plus, as we go from 1 to 2 and 2 to 3. But then from 3 to 4, let's go back to the good drawing. From 3 to 4, we have to take the 30 centimeters over there on the left and add it to the 1.5 meters in this dimension. So the total distance is 1.8 meters vertical. It doesn't matter that we go up and then down again. It's just the net difference between the two. So the net difference here is 1.8 meters, and it's minus, since we're going up through the fluid over there. So minus that pressure increment. And then we go back down again to A from 4. Ultimately, it should be 89.5 kilopascals. Okay, so who got that right? Good. Some of you, I think, are probably still working on it, and that's fine. But when you face these problems in the homework, I think it's just going to be the same process, that when you go down through the fluid, the pressure is accumulating. When you go up through the fluid, the pressure is decreasing. One student made a pretty interesting comment, and that is, you can calculate the pressure here. You can calculate the pressure here, and it's not the same as the pressure at A. So you could say, we'll go down through the water and then go down through 30 centimeters of mercury. Why is it that the pressure here and at A aren't the same if they're at the same elevation? Different fluids, right. So, you know, we went down through 30 centimeters of mercury, and the pressure accumulates pretty fast when you're going down through mercury. So when you're going up through oil, you're not losing pressure very quickly as you go up through oil, because oil has a low density and a low specific weight. So it's only the same pressure at the same elevation if it's the continuous fluid connecting those 2 points, if it's the same fluid without any change.
Now, is there any way to go from 2 and then jump over to the top of the bulb and then just use the 30 centimeters?
Nope, you got to go to the interface of the end of the mercury.
Okay.
Yep. Other questions?
You could go back to walk down.
Yes, you bet. Yes.
You were talking about like how it's easier, like the mercury, it gives you like a mechanical advantage. It's like more pressure as you go down with mercury, and then if you put oil going up, it's easier. Like you kept doing that, would it give you like less pressure?
No, no. What we like about mercury is just that since it's so dense, then the deflection will be relatively minor. But it's not like it's going to be generating energy by alternating the mercury and the oil. There's no like capacity there for it to do work.
So you just do that
Yeah, so why are we using mercury? We're using mercury simply so that we don't have to have a really long U-tube to measure pressures. You know, it's just the dense fluid is a tool that we can use to have a reasonable deflection delta H. All right. So did everybody get enough time with the solution here? All right. Great. Well, so those are U-tube manometers. There's also something called the differential manometer. So these U-tube manometers, you are measuring the pressure relative to the atmosphere. The atmosphere was the starting point because it was open on one end, just to whatever gases are out surrounding this manometer. A differential manometer, by contrast, isn't measuring pressure differences relative to the atmosphere, but rather the other end of the manometer is connected to the pipe. So any pressure difference that it's measuring is a pressure difference relative to some other location in the pipe. So look at this one. We've got some horizontal pipe, and here at 1, the manometer is connected upstream, and they're showing you with the arrow that the flow of the fluid is from the left towards the right. So now look at the deflection here. The deflection is that at 2, where it connects back up, whatever this manometer fluid is, they don't tell us whether it's mercury or oil or water, whatever it is, it's elevated on the right side of the manometer compared to the left. So what can we interpret from that? The fact that the manometer is lower on the left and higher on the right. Good. That's exactly right. So the fluid is flowing from high pressure towards low pressure. So how does this manometer tell us that the pressure is higher at 1 than it is at 2? Yeah, exactly. So there's enough pressure inside of this tube to sort of like push it more on the left than on the right. Now let me tell you something. The fluid isn't going through the manometer. The fluid is going through the pipe. We have moving fluid in the pipe, but inside of this manometer, conditions are static. So there's equilibrium inside the manometer. So it comes into some equilibrium and then the fluid deflection stops. So we got to be careful about that. Now, if the fluid was moving fast enough and there's a big enough pressure differential, it is possible that we could blow that manometer fluid into the main conduit. But for right now, it's in equilibrium. There is not flow through the manometer tube. But this is a differential manometer. And what we could do is we could measure the pressure difference by this formula. So the difference in pressure between 1 and 2 is delta H multiplied by the difference in the unit weights between the manometer fluid and the fluid of whatever's flowing through the pipe. But I'm going to put a big warning here. Not only did I italicize the warning, but I also underlined it and I bolded it. Because so many students have misused this formula over the years, I wanted to really drive home the point that this formula is only accurate when the pipe is horizontal. If the pipe isn't horizontal, then things get a little more complicated. All right? We'll look at that complicated set in just a second here, but what we're saying is that the elevation of 1 and 2 are equal. In that case, then the pressure difference between them, you can really easily calculate the pressure difference due to the deflection and the difference in the unit weights. By the way, why is the pressure higher at 1 than it is at 2? Why? Yes? No, it's the same elevation. Z1 equals Z2. Yeah. So at the pipe itself, not in the manometer. So why is it that here the pressure is higher than that? When a fluid flows through a pipe, why is pressure decreasing?
Friction as it flows.
Friction. Pipe friction. Yeah, so remember the no-slip condition? That diagram we looked at earlier in class where we know that as water or any fluid flows adjacent to a stationary surface, that interaction and the shear stress that's applied is going to reduce the energy that's available. So there's less pressure at 2 simply because as the fluid flows, energy is lost due to pipe friction. All right. So here's the more general, accurate equation that you don't have to worry about whether the pipe is horizontal for this equation that I just put up to be accurate. So it's explaining P sub z rather than P. So the top equation that's only true if the pipe is horizontal, that was P1 minus P2, which is by definition delta P is the delta H times the gamma of the manometer fluid minus the gamma of whatever fluid's flowing through there. But what I've just said is there's something else besides P. There's P sub z. Now P sub z means piezometric pressure. And that defined is the pressure at some location plus gamma times the z at that location. So if we're saying P sub z1, we're saying not only do we want to know the pressure at that location, but also we're going to keep track of its elevation relative to some datum. Just, whatever is the baseline that we're measuring our elevations against, not only do we want to know the pressure at one location, but we're also going to account for how high it is. And the reason why that's important is because pressure changes not just because of pipe friction, but also because of elevation. That's the whole point of the hydrostatic equation, right? Is that when you go down in a fluid, the pressure is increasing. When you go up through the fluid, the pressure decreases. And so pressure changes for two reasons in a figure like this. So now we've got an inclined pipe, and look at 1 versus 2. Okay, the water's flowing in the direction indicated by this arrow. The water's flowing from 1 towards 2. So why is the pressure at 2 lower than the pressure at 1? The manometer tells us the pressure at 1 is high and the pressure at 2 is low. So why is the pressure at 2 relatively lower than it is at 1? There's two reasons. Friction and gravity. Gravity being the hydrostatic effect, right? The fact that it's at a higher elevation, and so it's going to have less pressure simply because we're higher in the fluid. So for an inclined pipe like this with a differential manometer, what we want to do is we want to find the pressure at 2 and then the change in piezometric pressure. So what we have to do is apply the hydrostatic equation and work through this pipe to do it. So we're going to start where we know something and work towards the unknown. Okay, so here in this example, we know the pressure at 1. It's given. The pressure at 1 is 450 kilopascals. It's given that the fluid down here is mercury. Let's just use 133,000 newtons per meter cubed as the unit weight of this mercury. Delta H is 5 centimeters. Delta Z, the difference in the elevations between 1 and 2 is a meter. And let's see, delta Y. I don't remember. In this case, the thing about delta Y is that it cancels out, so it doesn't even have to be specified. So what we're going to do is, let me begin by writing it on the board, and then I'll let you take it from there. We're going from 1 towards 2, applying the hydrostatic equation through the enclosed pipe. And so the way it works is that P1 is where we begin, and we're going down through the fluid a distance of delta Y, so plus, because we're going delta Y, and then the unit weight that we should use here is the unit weight of water, plus delta H times the unit weight of water, because we went, first of all, down this distance, and then we're going to go down a little bit more. We're going to go down the distance delta H. So that's the second step here. And then that takes us to this interface, which is the same as there. And now I'm going to go up through the manometer fluid. So instead of plus, it's minus, because we're going to go up. So now minus delta H times gamma of mercury. All right, and now minus, because now my next step is to go upward the distance delta Y through this water. Delta Y through the gamma of water. Now I'm going to go up again, delta Z through water. And once I do that, finally that gets me to location 2. So all of that is equal to the pressure at 2. So this is, I know this is a lot of stuff. This is a really long equation here, but what we're saying is we start where we know something and we work towards the unknown, simply going step by step, hydrostatic equation. When we go down, the pressure is plus. When we go up, the pressure is minus. And eventually that gets us to P2. All right. So I've written this on the board. What I'd like you to do is look for terms, like terms that can be canceled out, because there are some things here where we've got a plus and a minus of the same thing. So cancel out the common terms, substitute in the givens, and find out what is P2 in terms of, how many pascals is it of pressure at 2. And then once you find P2, try to address the second bullet point here about piezometric pressure. The definition of piezometric pressure is the pressure at a location plus the gamma times the Z at that location. Okay, so here's the sketch. All right. So I'd already written on the board this part. Now, you're going to need to be able to synthesize something like this on your own. And the way that you synthesize this on your own is just that idea that you're starting where you know the pressure, the given pressure at 1, and you're just addressing all of the little incremental changes along the path inside of that manometer towards 2. And so you're starting with the given P1 and then increasing as you go down, decreasing as you go up. And we can cancel out some of the common terms here. And I think the common term that we can cancel out is the minus Y gamma of water, and then there was also a plus Y gamma of water. And that's why we didn't need the dimension of Y to be specified in the drawing. It's because we're subtracting and adding it. If we go back to the sketch, you can see here's the down through the water and here's the up through the water. And so that's why in the equation we don't have to know delta Y, is because we went down and up through water, so it ends up canceling itself out. All right. So then the substitutions. We've got our starting point pressure, increase a little bit through the water, decrease it a lot through the mercury, and decrease a little bit more through the water, and that gets us to P2. Okay, as I was walking around, it seemed like a lot of people were getting this 434 kilopascals, and that's right. Any questions on this first part of the problem? All right. In the second part of the problem, I asked you to take a look at the change in piezometric pressure. So applying this formula. So between 1 and 2, we know the change in pressure because it went from 450 to 434. So the pressure decreased for 2 reasons. The pressure decreased partly due to pipe friction, and it partly decreased because of the elevation change. What this piezometric pressure allows us to calculate, if you calculate the change in piezometric pressure, this 6,160 approximately pascals, that is the component of the change that's due just to pipe friction. It's just measuring how much pressure change is due to the pipe friction, and it's not influenced by the difference in elevation. So the way that we found it was just the delta H times the difference in the unit weights. And let me try and explain it in a way that will help this make sense. Think about if the water wasn't moving between 1 and 2, if we stopped the flow, like we've got some sort of a valve and we close the valve so there's no movement in water, the deflection would stop. There would be no reason for this delta H. And so the two elevations would be the same if there was no flow of water through the pipe. And so I hope it makes sense that the only reason why there's this delta H is because of pipe friction. It's not because of the difference in elevation. So that change in piezometric pressure is a way of measuring the impact of pipe friction. Yes?
So can you also get the change by finding piezometric pressure of 1 using the other formula? Do the same thing at the second one, just taking the difference?
So you're saying before we solved the problem, find the...
You find P1 and you find P2.
Uh-huh.
Those to piezometric.
Yes.
Just do it that way.
Yes. Yeah, you'd get the same answer because, you know, we know the Z. If we said, let this be Z equals 0, and that would be Z equals 1, yeah, you'll get the same answers if you do it that way. Other questions? What? Because it's 5 centimeters. In this piezometric equation? So you're saying why is it delta H and not the whole height between 1 and 2? Ah, it's because piezometric pressure only accounts for the energy loss due to pipe friction. Question over here? Okay, it's because think about the case of what if the water wasn't flowing. So if the water wasn't flowing, if we stopped the flow through the pipe, then there wouldn't be a delta H. And so if we wanted to know the absolute change in pressure, then we would have this Z2 minus Z1. But you know, piezometric pressure is, by definition, something different than absolute pressure change. Yes?
I thought we could only use that equation if the pipe is horizontal.
No, we can only use it to be the change in pressure if it's horizontal. So the change of piezometric pressure is always valid. But when it's horizontal, Z1 and Z2 are equal, and so the change in piezometric pressure is the same thing as the change in actual pressure. I'm glad you brought that up because that's a point worth repeating. So in this case, since it wasn't horizontal, this formula is measuring the difference in piezometric pressure, not the difference in absolute pressure. All right. Now, we've been talking about pressure a lot the last couple of days. There's also a different way of thinking about pressure. It's just a different unit system for measuring it. And it's called head rather than pressure. And what you do is you divide the pressure by the unit weight of the fluid. Let me blank this up because I'd rather have your attention on the whiteboard for just 1 second. Remember when we were talking about a piezometer? We've got this pipe with the alternate conduit sticking up out of it, and the water level rises to a certain elevation. Okay, so this was the piezometer. That's what this device is. So this device is a direct reflection of how much pressure is in the pipe. There's some pressure here. Well, some people decided that instead of measuring the pressure, you could measure how high the water level would rise, and they call that the head because it's sort of like the head of the water poking up out of the pipe. And the similar thing is true in wells, that if you have an artesian well or like a geyser, that the groundwater is under pressure, the water level will rise to a certain elevation. So rather than talking about pressures, sometimes we talk about head. And remember that the formula here, the delta P is delta H times gamma. So delta H is delta P divided by gamma. So sometimes we have the head that we talk about as an alternate means of measuring the pressure, and the units of head are meters. Okay, so here, piezometric pressure versus piezometric head. Now here's piezometric pressure. If we divide each of these terms by gamma, then what we're left with is that we have piezometric head is the pressure divided by gamma plus the elevation. So you can rearrange the difference in piezometric pressure to instead be a difference in piezometric head, and we'll end up with this formula. And this is maybe just sort of like a foreshadowing of things to come. You're not actually going to need to start solving problems quite yet with piezometric head, but later on, particularly when we get into Chapter 7, we'll talk about the head in terms of how much energy there is available for generating electricity, for example, in a hydropower system. But I just wanted to introduce that as a beginning idea for now. All right, so let's change gears a little bit and talk about pressure variation in the atmosphere. Here is a picture of a weather balloon, and they're about to launch this weather balloon. It looks like there's a lot more plastic there. They could have put more helium or hydrogen, whatever it is. Why didn't they fill the balloon up all the way? Okay, to control the rate of descent. Maybe they don't want it to go upward too quickly.
More surface area would make the balloon get
Okay.
carried further
So
away.
maybe if it was too big, it would get blown more easily. You have another idea?
The higher it goes up, it starts to expand.
All right. And that's another really important point, is the higher it goes up, the more it expands. Why? Why does it do that? I'm sure when you were a kid, you probably let go of a balloon, and eventually it pops. Why does it do that? Okay, as you go up through the atmosphere, there's less pressure, and so a certain volume of gas is going to expand. In other words, the space occupied by whatever gases are in that balloon is going to increase because there's less pressure holding it back on the outside of the balloon as it goes upwards. Why is there less pressure as you go up through the atmosphere? It's gravity. It's for the same reason that pressure decreases as you go up through a liquid. It also decreases as you go up through a gas, and our atmosphere is a gas. So here is another reason that helps address why pressure changes, and this is a figure that's showing the average temperature of the atmosphere as you go up in elevation, and this is called the lapse rate. And inside of the troposphere, which is the layer of atmosphere closest to the Earth's surface, there's approximately a linear variation, so that when you go up a certain elevation, the pressure is decreasing, and it's pretty constant. This lapse rate, abbreviated alpha here, means that we can calculate the temperature at a certain elevation by just taking the temperature at a known elevation, and here's that known elevation Z0, and then if we go upward, we'll find the difference in elevation between the 2 points and multiply it by that rate. Here it's saying that on average you're decreasing about 5.87 degrees Kelvin for every kilometer of elevation that you go upward. Now, this is a little bit more sophisticated way of addressing how the pressure changes because of that temperature change. And so what this accounts for is the gas constant for air. You'll notice here as an exponent, we're going to keep track of the gas constant, and we have a difference in pressure change, and gas volumes change because of temperature as well. And so the pressure as we go up through the atmosphere is going to be affected by not only the temperature change, but the volume that that balloon is occupying is going to also increase because the pressure is decreasing as we go up. Yeah?
Is the G equation just gravity?
Yes, G is gravity. All right, so just to try this equation out, how many people here have ever been up on the Burj Khalifa? Just me? Just me? It's awesome. I've been up there several times. And the crazy thing is that the observation deck is just over halfway. They don't even let you go to the very top. Those are like super exclusive apartments up there. But anyways, I shelled out my money and I went halfway up, and it looked pretty tall. But there's a deck where you can actually go outside, and it is noticeably cooler. Now, how much noticeably cooler? Let's just try it out according to this lapse rate equation. Let's say that at the bottom of the tower, it's 30 Celsius, and that the bottom of the tower is about 10 meters above sea level. And here we've got some assumed pressure at the bottom. And let's say that we got lucky and we went all the way to the top, 828 meters tall. So what I'd like you to calculate, first of all, is what's the temperature at the top of the tower there. And so if we go back to here, the temperature aloft is the initial temperature minus the lapse rate multiplied by the elevation difference. And so the temperature aloft will be the numerator of what's inside the brackets there. And then also I'd like you to use the full equation to estimate what is the air pressure at that higher elevation. All right, so let's take a look at the solution for this one. Okay, so the temperature aloft at the top of the building, first of all, we have to find the difference in elevation. So the difference in elevation is going to be 0.828 kilometers, since we're going from 10 to 838. And we have ultimately a temperature of 298.27 Kelvin up there. That works out to 25 degrees Celsius, so it's cooling off as we go up. Yeah?
I thought the distance was 828.
Yeah, it's 828, but the base of the tower is at an elevation of 10 meters, and so the top of the tower will be at 838. So the 838 comes from the 10 plus the height of the building. All right. Now, for the next part, we're going to apply this air pressure at the top approach, but I'm now not so sure that I did it right. I'm going to have to double check the units of this exponent factor here. What I had intended is that, if we calculate this unitless exponent factor, then you end up multiplying the ratio by the initial pressure, and if you just do all those calculations, it's 88.4 kilopascals. But what I'm going to have to do is double check and get back to you on whether the units cancel out here or not, because as you'll notice, this is Kelvin per kilometer, but all the other units are in terms of meters. So give me a few minutes to double check on that, and I'll email you after class. We're after 12:16 right now, so we need to finish up. Let's just review the announcements here. Your assignment due on Tuesday. Here's the assignment set. Upload it to MU Online before 11. And let me know if you've got any questions. I've got office hours today until the afternoon.